Hopefully everybody's fresh back from lunch. It's my job to introduce you to the energy part of the day and to give you an update on our thinking. So first things first, we have a project name. It's called Empower, short for Elastic Management of Power, and I hope that empowers us to success. We also have put our thinking in writing. We have a position paper called The Case for a Cloud Power Control Plane that you can find on the FOCI website. We also have a bigger team, so thanks in particular to Jonggyu and to Theano for helping us write the paper, and also a big shout out to all of the students who have either already started a project on energy management and power management or are very interested in starting a project, so may start a project soon. Okay. So a quick recap, why is cloud power control important? Why is it important now? Couple of reasons for this. The first one is the rising cost of data center power infrastructure. We've already heard this a couple of times today. This actually goes both into the kind of large-scale grid infrastructure, where it's now becoming table stakes for new data center deployments to be able to support some level of elastic power control, or demand response as that's called, to stabilize grids. So this is in particular already true for locations like Ireland and Virginia, where there's a lot of data center concentration already, mainly because the transatlantic cables end on both of those sides. And so data centers make up already a large fraction, I believe it's more than 1/5 for, say, Ireland, but it's very similar in Virginia, of the power grid. And so in order to stabilize the grid, the only way to still deploy new data centers in those areas is to actually cut a deal with the utility providers to guarantee that the data centers can be elastic and can respond by reducing demand when there is some variability in supply on the grid. The same thing is true for the power distribution infrastructure inside of data centers. As we build larger and larger data centers, that infrastructure also becomes more expensive, and is one of the most expensive parts of any new data center deployment. And so data center operators have already been asking, well, could we somehow maybe oversubscribe that infrastructure, not deploy as much as we think we may need once we deploy more servers, and then do some kind of dynamic response inside of the data center to adapt. So that's one reason. Another reason is this drive towards renewable energy. Dave Patterson said it this morning. Basically all cloud operators, certainly everybody who's in this room, wants to be 100% renewable powered roughly by the year 2030. Short aside here that Dave didn't mention is that the demand for compute currently actually rises at 2x the deployment of new wind and solar generative power. So if those trends hold, that should mean that in order to be 100% renewable, we would actually have to operate within a mix of renewables and fossil fuels and then purchase offsets. But regardless of what's going to happen, with an increase of renewables in the power supply mix, there are swings of how much of that renewable power is being generated, simply because wind and solar, the two primary sources of renewable energy, have these production swings because the sun has to shine or the wind has to blow. And if we want to get close to 100% renewable without purchasing so many offsets, we'll have to be able to adapt to that. There's also an increase in power disruption, mostly due to more natural disasters, which is attributed to climate change. For example, and these are already numbers from, I think, almost 2 years ago. Now I need to update these. The data center operators have been observing grid failures at about 4x those that were predicted by the kind of specifications for the deployment of commercial and industrial power systems. And similarly, the mean time to recovery on the grid side is 4.5 times above what is usually assumed to be normal operations. This is generally worse for rural locations, for developing world scenarios, where there is a lot of growth happening right now in data centers. It's also known as the edge in data centers, where there's a lot less resiliency in terms of how many providers I can choose from as a data center operator. And then finally, there's just simply resilient operations and logistics. There's such a thing as a black swan event, as it's called by data center operators. COVID was one very big one, where there was a massive power demand increase due to massive workload demand increase because everybody was moving online, and that was one of the hardest problems for operators to solve. Not so much provisioning more servers into data centers, but actually powering all of those servers. And we are now observing something similar with the LLMs having made such a splash that is now fueling yet another massive power demand increase. And so we have to understand power consumption in data centers better and also control power consumption in data centers better. So more specifically, we have kind of worked out a couple of the scenarios that are becoming challenging to data center operators from a pure power perspective. And so these graphs here show you power demand and supply over time. Here's a scenario with variable supply due to an increase in renewables in the mix. Say you have this demand curve here for your data center, and that may hold pretty steady today, but you have these swings in renewable energy supply. Sometimes you may actually have a lot more renewable energy available to you in the grid than you can currently absorb, and that is something that you may wish to actually absorb. The grid operator may want that from you because it's one way that they can stabilize the grid, but you may also want to just make use of all of that technically free energy at this point. The grid operators maybe even in some areas pay you for consuming that energy. And then similarly, there are scenarios where the only way you can actually power your data center are by having an increased amount of fossil fuels in the mix, which you would like to minimize. Another scenario are demand spikes. These could be due to these black swan events, or simply because you're oversubscribing your internal power supply infrastructure, so you're operating very close to the supply, and then you have the spike in your workload, and suddenly you can't meet that demand with that data center because it would require too much power and you would trip breakers. Finally, there are blackouts and brownouts where suddenly the power could be massively reduced or even go out completely from the grid. And so you may be operating on reserve power. Of course, batteries and flywheels and generators have limited capacity. And we have already had scenarios, such as during the Texas winter storm, where data center operators were at the brink of having to shut down the data centers because there weren't no further reserves available. And so that is also a problem because data centers are often part of critical infrastructure. A lot of kind of first responders in these emergency scenarios actually rely on massive amounts of compute as well. And when they don't have that available, they're not able to actually help people in these areas. Yeah, and so because of these challenges and to overcome these challenges, we would like to empower the cloud to be able to be elastic and to change its power demand. And so in order to do that, we have to make cloud power demand software defined. So think about this in a similar way to how we have made networks and other parts of our infrastructure software defined by basically being able to build software that can execute automated power control policies and react to these scenarios very quickly and then adapt the power demand at large scale within data centers. In order to make that work, you might imagine we need some sort of feedback loop through the hardware-software stack. We need to firstly have a better understanding of how power is being consumed in data centers that can then inform controllers, maybe other parts of software that can then adapt to this and then also control the amount of power that is being consumed, say, from the operating system to have some sort of coordinated power control for servers and so forth. I'm going to go into some more detail a little bit later in this presentation. So yeah, we're building Empower, which is also the name of our system, which is going to be this control plane that can observe and control power demand, ideally at very fine granularity, and also over quite short timescales because some of these events may be quite unpredictable. In order to do so, we will leverage some slack that we will have in the SLAs for applications. Basically, we understand our applications better as well and what their requirements are. There may be some that are quite critical. Those will be hard to kind of move aside. But there will also be many that don't have those sorts of requirements. And so those are application loads that we can shed or shift in the data center, time shift in the data center, migrate them potentially to other data centers in order to then power switch hardware components to save power. And so with that then, we're hoping to be able to do these adaptations by introducing shiftable demand. This could be time shiftable or space shiftable demand. So here's one solution for variable supply, where we can now leverage all those renewables and minimize the amount of fossil fuels we're consuming. We can adapt to demand spikes by shifting uncritical loads away and giving priority to those critical loads. And we can also potentially outlive blackouts by effectively shifting everything that's non-critical and just executing critical loads during the time that we're in a blackout to prolong the lifetime, the capacity of, say, the generators that we're operating off of in these blackout scenarios. And so we've identified 5 particular challenges that we would like to solve in building Empower. The first one is that we observed that there is actually a quite limited power control dynamic range within current data centers. This counts in particular for data center servers, which are one of the major consumers in any data center. So it is true that there is some limited amount of dynamic range we have due to techniques like dynamic voltage and frequency scaling. There's also Intel's RAPL, which allows us to control the kind of CPU uncore side and the memory side of it. But we find that there's actually a massive amount of idle power that servers are consuming. So even if we manage to shift all load away from a particular set of servers, the cores would kind of throttle and reduce their power consumption. But we measured that servers can have up to, for regular servers, not GPU servers, up to 220 watts of idle power consumption. And we actually found that that trend is increasing over time due to an increasing number of kind of I/O devices, heavier weight I/O devices like SmartNICs that are being integrated and so forth. For GPU servers, this actually can go up to like almost 600 watts of idle power being consumed when there's nothing running on these servers. So we'd like to overcome that. Secondly, it's the case that current software stacks actually have only very coarse insight into how power is being consumed. There are some power instrumentation interfaces. Again, RAPL is one that allow us to measure power being consumed at the, say, socket level, and then there are also board management controllers that report the power consumed at the wall socket, basically at the chassis level. But ideally, if we want to really have good control and knowledge about which workloads we want to shift, we need to know and break down this power consumption into the applications that are actually running on top of these servers and their consumption so that we can make smart decisions. Should we rather move this workload over another workload away from the server in order to reduce its power consumption? There's also limited integration right now with accelerators and I/O devices. Pratyush is going to give a talk later in the session about looking at GPUs in particular and their power consumption profiles and what to do there. But also other I/O devices and storage devices and so forth have the same kind of problem where there's currently very limited insight and limited control over how they consume their power. And so we would like to bring these interfaces to the operating system so that we can actually have some form of coordinated power control, perhaps. So we know these workloads are not going to be using the following devices heavily, and we can reduce their power consumption. And finally, of course, we want to be able to operate at scale. So that is another problem that we have. So then here is a brief overview of our thinking as to how this may integrate into a data center. My apologies, this is a little bit crowded figure. I'm going to try to start here. First, at the bottom, so basically what this depicts is a number of data center servers that are integrated into a larger scale factory-style data center network. And there's going to be some master controller similar to kind of like an open flow networking controller that is a centralized, somewhat centralized entity that can get all the data and make decisions. But let me actually start here at the bottom. We intend to kind of modify the operating systems and hypervisors inside each of the servers in order to do this fine-grained characterization, for example, of the applications, do the attribution of chassis power, socket power, to what the applications are actually doing and to what extent they're each doing it. We also want to build mechanisms that allow us to much more nimbly and with much greater dynamic range control the power, including all the way to node shutdown. But also at this finer coordinated granularity of the different I/O devices that sit inside of a server. We're going to build operating system support for that. And finally, we're going to look at offloading some workloads into low power CPU devices as well. I'm going to say a bit more about the first three. I'm going to leave that out to not steal Pratyush's fire later. And then eventually this is kind of all reported up to the master controller through the data center network, which also gets information from the supply side and can then run policies to determine power budgets that are then distributed back out to the servers. This is primarily to support scalability so that each server can act locally under its budget, and we don't have to route everything through the centralized power controller. In the limit, we could even do this directly on programmable switches and so forth, but we're taking a step at a time. And so yeah, then just a quick intro to some of the things that we have started to look into. So the first one is to kind of enlarge this power control dynamic range by allowing hosts to be shut down. And so the idea is that we can do so remotely by sending these hosts IPMI signals, but we want to be able to bring the hosts back quickly when we need them again. And so we have looked into what the current kind of state of hibernation in operating systems for servers is. And it turns out that hibernation is not an area that has been particularly researched for servers. It's primarily something that is done for laptops and other home devices that run off battery. And so the current state of the practice there is that Linux will effectively, if you put the system into hibernation, will store a system image just at that time. That will take a while. You can imagine the server may have terabytes of memory, will take a while. And then when you start the server back up after the BIOS has run through, it will restore that image back from what it thinks is a block storage device. So we want to make that a lot more nimble. And our idea here is to use CXL to accelerate both effectively by leveraging the fact that CXL is load store accessible so that we may be able to directly execute out of a CXL stored memory image that has been kept alive while the server was shut down to accelerate startup times, but something similar we can do to shorten the shutdown time as well. I'm not going to say much more, not to steal Jonggyu's thunder, because he's going to talk about this right after me. Another one is to do this much more fine-grained power instrumentation. Ideally, we would like to break this down into like per container, per process, perhaps even per RPC power consumption. The main reason for these levels of granularity is that they allow us, or these are the granularities with which we can control power demand. For example, we could reroute RPCs to a smaller number of servers once we have shut down processing on one side of our data center. And so that's why RPCs are interesting. And then similarly, processes and containers and also virtual machines are the units of compute that the users typically deal with. And so here the idea is to take these measurements using the hardware infrastructure that's already there. So this includes socket and CPU level measurements, augment that with performance counter measurements, and then build models that can map these measurements, these performance counter measurements, to power consumed. And so we're building a tool right now that makes that happen effectively by taking a couple of measurements, stressing the system in a variety of ways, and then training ML models. We're trying a bunch of them, and we have some good early results of a mean square error within just 10% of being able to, after we've run these kind of synthetic benchmarks that stress the machine in a variety of ways, to then say, here's an application, here are the performance counter measurements of this application, to then say, here's the power that this application consumes. In the interest of time, I'm going to skip the detail on that. And then finally, we're also looking into more fine-grained coordinated power control. For example, we intend to build a power proportional storage service, something like Amazon S3, where you can imagine there's a whole bunch of storage devices behind the storage service. And we would like to have the software on that storage service understand how power is being consumed across all of these heterogeneous storage devices. And that then also would allow us to shift power consumption essentially by shifting where data is temporarily stored or buffered inside this hierarchy of storage devices in order to save power. So one idea would be if we find that hard disk drives consume a lot of power, then because they're mechanical devices and so forth, they're mostly used for high capacity, kind of longer term storage. We could say temporarily, let's shut them down and not use them for a while to store all these writes. These are also very write intensive devices, and buffer these writes inside SSDs, for example, for a while. And that would be one way to trade off the power properties of one device for the power properties of another one at kind of service level. Okay, I'm running out of time, so I don't want to take up more time from postdocs and students. So in summary, cloud power consumption is increasingly a problem due to the reasons that are already laid out. Our goal is to make the cloud power aware by building this power control plane called Empower, which then brings about a much greater dynamic range in power control, but also power accounting, ability to debug power consumption, instrument at scale, and fine-grained and coordinated power control as well through the building of software services that can coordinate the power consumption across a potentially large number of devices at scale in the data center. Thanks very much. Any questions?
Thanks, Simon. That was great. What did you think of Dave Patterson's talk this morning?
A great talk. I think he did not, in case I'm just going to take the antagonistic viewpoint and say, I don't think he said anything that said that we shouldn't bring power under control, right? Because he focused specifically on machine learning workloads and was basically saying, okay, there's this big scare that ML workloads would be the thing that would blow all power consumption out of the water. What he said is, well, if taken as just training on accelerators, the fraction of power consumed versus the rest of the things that a data center typically does doesn't change. It stays fixed. But he did say multiple times the pie gets bigger, right? So all of the things that a data center does, and this is perhaps one reason why we're looking at servers generally, but we're also interested, of course, to look at GPU, and Pratyush is one example there, is that of all of the things that data centers do, the cloud is much bigger than just ML. There's a massive growth in power consumption.
So I get the approach of leverage the fact that power is not proportional to concentrate workload in some places and thereby try and reduce total power consumption. That makes sense to me. The other thing that this work almost always leads to is the recognition of, hey, can I pay less money to build out the power trains because I should be able to stat mux power. And in networking, when you stat mux networking and you temporarily oversubscribe an output buffer, you drop some packets and things go fine. But with power, if you oversubscribe a circuit breaker for more than about 5 milliseconds, it trips, and now you have this huge problem. So I didn't hear you sort of talk about that second part. Is that part of your agenda?
We do have to have guardrails to not trip breakers, right? So, I mean, I'm sure you're aware, because you're probably doing this yourself, is that data center operators are already oversubscribing power infrastructure. There were a couple of papers, not by Microsoft, but Google and Meta both had papers on this. And so that means we already have to be careful not to trip breakers. So just to say that it's possible not to trip the breakers. But you're right, we definitely have to make sure, this is one reason why we have to be able to act at short timescales, that if we see that we would trip this breaker within the next 5 seconds or so, that we definitely make sure that we're not consuming any more power on that rail.
Milliseconds, right?
And potentially milliseconds, yeah. So I mean, the goal here is to try to bring this down to that level. We're not quite there yet. We're going to see if we can bring it to that level. I think if you're worried that we won't get it there and thus this whole agenda may fall apart, I think there's the answer to that is you just have some buffering room, right? So you do then reduce the envelope within which you can control, the dynamic range within which you can control power, to make sure that if you cannot react within, say, 5 milliseconds, that you are within a window where you know that until you reach that level where you're going to start hitting the breaking point, the tipping point for the breaker, that you had enough time to react. So you got to reserve some headroom at that point.
Isha from Azure Systems Research Group, and as you know, we're doing a lot of this work as well. So my question was on the SLA. The way you talked about it sounded like it's more at a container level or at a service level within the node, right? Are you also thinking about it at a service level that's sort of distributed across many servers, or at a subscription level, right, for a cloud provider? Because that then loosens the restrictions by a lot in terms of your SLA. If you also are able to give some feedback to the workload in terms of load balancing and stuff, that can open up a lot more opportunity.
It's a great idea. I have to admit, we haven't thought about it at that level yet, but I think that makes perfect sense. Ultimately, it's about the user's demands, right? And they will operate at a much higher level than just like the individual processes and so forth. So that's why I think that makes sense. Plus, it makes sense to maybe kind of leverage the market forces and just kind of give back to users if we do end up violating, or like have incentives for them to make their software more green, but then in exchange take a certain slack into account, and those kinds of things absolutely makes a lot of sense.
Can you pop up the graph that you have where the first of your graphs explain where the benefit is when you're oversubscribed, when you have fossil fuels on the bottom, and yeah, that one.
This first one.
Yeah. So the benefit, the opportunity that you can extract here is the difference between, or the ratio between the rectangle defined by the peak available compute and the area under that curve.
Yeah, I mean both of these, right? You want to use this energy, and you want to not use this energy.
If the shallow parts weren't very low, then there wouldn't be much to do here, right? You'd be operating very near your capacity. But that ratio, as that gap gets bigger, that becomes a problem for your embodied carbon, right? So now you've got a whole bunch of resources sitting around doing nothing most of the time because you've carefully turned them off. So it seems like you're directly opposed. Like I don't know what to do about it. I don't have any great advice, but like it seems like there's an inherent conflict. You either buy enough resources that you can take advantage of this peak power and then leave them turned off, or there's actually not very much opportunity because you're leaving them on.
Yes, so I think viewed from the carbon perspective, there is the embodied carbon problem. I would say though that this is a phenomenon that's already happening, right? Because you have a data center that you want to deploy of a certain size. And in order to play with the utility, to even be able to deploy it, you have to give them this concession that you're going to be adaptive to the power supply. And because of oversubscription and so forth, this is already happening, right? Yes, but there is this inherent trade-off with the embedded carbon that you have there as well. You're going to deploy a certain amount of hardware, knowing that you're not going to utilize it all at the same time, which, I mean, even if you look at kind of way back, the kind of standard adage for data centers is that most hardware is only utilized to like 50, 60%, right? So there's also that same problem embedded within it is you pay for this hardware, both in monetary cost, but also in embedded carbon cost. But you're only using it effectively half of the time, right?
So it sounds like you're saying this is an inevitability.
It's a perennial problem, yeah. Yeah.
This is Dan from Azure Research. I disagree with that characterization. Like we've looked at the gap of like how much is unutilized, and just using that for that, it didn't seem enough. Okay. So the answer to that question, like what do? You have to model it. I mean, you have to explicitly have embodied carbon cost models and operational carbon cost models. You have to really quantitatively make that trade-off. I don't think there's any way, like back of the envelope, there's enough space, blah, blah, blah. You really have to model it and be very careful about it.
And to be clear, I'm not against modeling it, right? I mean, that's definitely.
But I think if you say, we can hide behind the other problem, I think that leads you down the wrong path.
Sure, no, and I didn't mean to say that. Sorry if that was the impression. Obviously, that's an important problem as well. I just can't solve all problems at once. So hopefully, we'll find some way to reduce the embodied carbon. I mean, there's kind of your approach of kind of leveraging old hardware, right? So like taking old DDR modules, reusing them, can also allow you to have kind of a vast amount of resources in the data center that the embodied carbon was already paid for once, and you're not amortizing that cost, right? So that could help. Thanks, Andrew. You can also use that.
Hi, I'm Jonggyu. I'm a postdoc researcher working with Tom and Simon. Today I'm going to talk about our effort to reduce idle power that Simon explained already using the new CXL technology. So data centers are using energy a lot and expected to grow a lot due to partially like new applications such as machine learning now, or like more powerful hardware devices such as GPUs or something like that. So it's a little bit outdated, but as of 2020, so data centers actually use up to 400 terawatt hour, which is around 2% of the world energy consumption. And that is going to be increasing gradually and kind of like faster than ever So expected to be 4% as of like 2030, but we presume like it's going to be higher than that because of the machine learning things or new hardware technologies. So one of the problems in that data center power consumption is idle power. So actually a large amount of data center resources are idle most of the time. So if you really try really hard, maybe you can run the data center at around like 50% of utilization, which is really, if you really try. But mostly like less than 40% or less. So the idle power itself actually comprised like 40,000 gigawatts hour in 2020s in the United States, which is really a lot. So we were curious about like how idle power actually, like how much it is. So we used a bunch of like various machines across inside the cloud lab or our local ones. But it turned out recent advance in hardware and software is not sufficient to radically reduce idle power. So like, for example, like local machine B actually it's a like kind of many core machine. The idle power itself is 220 watts. And if we attach more I/O devices or something like that, it's gonna be expected to even higher than that. And of course, like GPU servers require much more idle power. The other one is like power proportionality. So like with the multi-decades effort to increase power proportionality, which is mostly focusing on CPUs, data centers are like still somewhat a little bit of proportional, but it's not that like 1%. So which means like it's always better to keep the machine as busy as possible for energy efficiency. But the problem is most servers and data centers are underutilized, like around like less than 30 or 40%, like in terms of like CPU utilization. So the problem is, as I said before, it's always better to increase the CPU utilization as much as possible. Otherwise, the energy efficiency decreases. So most of the data centers are into like some energy inefficiency zone described in the blue box. So previously, this is mostly for power over subscription, but to control power consumption, there can be software effort, which is one of them is bandwidth control. So it is like throttling available CPU bandwidth to reduce power under the particular power cap. The other one is core jailing, which is like isolate processes into a subset of cores and leaving other cores into idle, so that like they can actually reduce the total power consumption. But the problem is, again, that means like they put into really low utilization, which in turn into like really low energy efficiency. The other one could be just shutting down or hibernating servers. Just shutting down servers can be really fast, but the problem is that you lose all the states. So you need to load all the necessary components to run an application or something. But the current hibernation takes really long time because they are designed not for data centers or like some fast whatever things. So it takes really long time to save states on the critical path. And then restarting also takes a lot of time. So we view recent computer science change as opportunities. So from software perspective, things are changing into Microsoft architecture, which is where an application is broken into multiple small independent services that actually makes it elastic and distributed architecture. So which is easier to migrate or shed computing node in a better way. The other one is like serverless architecture. The market is actually growing each year. So the serverless architecture, we believe that brings greater control over the workload selection or migration or something. So it actually makes it easier to make easier allocation of workloads to proper machines, other than just like borrowing the bare metal machine or like allocating VMs. The other one is like, the other opportunity from hardware perspective is CXL. CXL provides multiple interesting features, including memory pooling, which actually we can use a large space of like byte addressable memory across nodes. Also, we can use load store operations. The other thing is the memory sharing, which is actually multiple computing node can access simultaneously data on the CXL memory across machines, which actually makes it much easier to migrate VMs, which is not currently done many times or something. So the goal is we want to leverage the ability of CXL and the current the changes in the software platform. So we want to build a new hibernation mechanism for several machines using CXL technology. So first we want to build a write-through system memory mechanism to CXL during the normal operation time, which actually which will allow us to reduce the hibernation time. Also, we want to do a bunch of other operations or optimizations to quickly boot up the system and then restore the previously saved state. So this is the current conventional hibernation process. First, they don't support more memory such as CXL, and everything is on the critical path. So if you click hibernation, what they do is they first create bitmap and hold all the processes and save process states, and then save creating headers or something and save all the things into swap space. So they take really long time. So what we want to suggest here is we want to make it really fast to do hibernation, also really fast wake up. So to do so, we first want to make build a write-through kernel method, the daemon, which is this. So what it does is we gradually synchronize the current system image into the stored system image. So to do so, we build a kernel daemon that periodically traverses the page table and then check the 30 bits and then synchronize those kind of change data into the stored system image inside CXL. And then once we want to hibernate particular machines, what we have to do is only just check what kind of data pages are changed in the meantime, and then we save only the 30 pages into that hibernated the system image, and then we can just shut down the server. This is the early version of the system. We tested the hibernation cost in terms of time. So to hibernate to save this kind of data into hard disk drives, it took around 2,000 seconds to save 150 gigabytes of system memory, which is unacceptable. But we could reduce that to 6 to 7 seconds because we already saved all the important data into the swap space in advance. So we also tried another experiment with a different machine with Optane persistent memory, which is much faster than hard disk drives. So the conventional hibernation took around 500 seconds in the case of 450 gigabytes of system memory. But we reduced that to 38 seconds, which is around 13 times faster than conventional ones. So this is still early stage of the project. So what we further want to do is we want to design a new efficient system image format other than using the conventional naive one to make it better. Also, we should support for CXL pulled remote memory. And for the fast wake up, we need to build an incremental image loading mechanism that we don't actually want to load all the system images at the same time because it takes really long. What we want to do is we want to separate hot and cold data, and then we want to bring hot data first into the local memory, and then the necessary image components that we readily need to run services. And then the other thing we can also do is there will be a lot of different kinds of stories and different kinds of speed or characteristics. So we want to leverage that by having a hierarchical image store, so that we can, if the machine should be booted up really quickly, and because they are running a really important services, then we can maybe store the data into either local flash memory or remote CXL memory. Otherwise, maybe if we can delay the slack, then maybe we want to store those kind of data into disaggregated storage, which takes more time than other ones. So in summary, data centers use a lot of power, but most of them, I mean, not most, some of them are actually idle power, which we are just wasting the energy. So what we want to do is we want to use the CXL technology to reduce the idle power, and then also upon certain power events, we want to radically reduce the entire power consumption within really short time period. So to do that, so we are already building like some hibernation schemes, and we are planning to build some other techniques to boot up or restore the system image from the CXL memory. The early results shows like around we could reduce the hibernation time by up to 13 times. Yeah. Thanks for listening.
It seems like you may need some amount of application cooperation for me to be able to hibernate the server.
So let's say like we have like multiple VMs, but we don't need it right now. Then we might want to like migrate the VMs into other ones, and then we want to hibernate the entire server so that we can reduce the idle power.
So like phase 1 is make the server idle.
Yeah.
Phase 2 is hibernate it.
Yeah.
Okay, I guess okay, that wasn't obvious.
So because we want to reduce the idle power, so that means like the server is already idle.
Okay.
That will, yeah.
Okay.
First, a comment on the making servers idle. That is such a valuable thing, even not just for power consumption.
Yeah.
If you can find a way to make servers idle, like idle servers are the most precious thing in the data center. You can do firmware updates. You can schedule any workload on it. Like super, super cool if you can get there, even without power. Okay. The other thing may be similar. I was a little bit confused about some of the details. Like, for example, what CXL version are you actually assuming? So I'm saying that because in what device type, like in CXL1, it's all managed through the BIOS. So that would probably be up before the OS, so you can access the CXL memory. So that's good. CXL2, it's all OS managed. So there might be a race condition when you start up. I don't know how that happens. Second, depending on what CXL device you use, you could use a Type 2 device. The device can flush all the caches on the CPU without the CPU having to do anything. So why do you have to do anything on the CPU? I think there was, maybe it's just the details you haven't explained, but yeah, I didn't understand why this design point and what do you assume?
Maybe take this, right. So the good point about CXL 2.0, like I think this assumes right now kind of memory expansion scenario, like CXL 1.1 style, where it's basically hardware managed, and so you can just execute straight out of that expanded memory. Obviously, if there's more that needs to be done for 2.0, maybe we need to have some sort of thing that comes up first. Maybe just a stub like a bootloader kind of thing that starts to control it. The CXL device maps the right things in and then cooperates with the kernel to be able to bring the image up. That's a good point. 2.0 would allow us to kind of also leverage it to migrate workloads from one server to the next in order to kind of bring about this idleness more efficiently, which is why I think we do want to look into that, to kind of pool memory and use it for that purpose, to migrate workloads. Sorry, there was a third thing that you said that I had.
Why not use a Type 2 device? Why are you using
Right, and I think that's a question of offload. Right now we don't have any Type 2 devices to play with. So that's why we went for this design where the work is being done on the server by the operating system in the background, but sure, it utilizes some CPU resources to do a minimal, but it does. Yes, I would imagine that if we had compute on the far side, we could actually then use it to just pull this and have it be completely transparent. At least transparent in the sense of it doesn't take any cycles on the CPU side. I would imagine you still need some kernel support in order to do that bring up for CXL 2.0 and onward.
Do I understand correctly that the way you're getting this benefit in reduced latency for hibernation is that you're constantly writing through during the workload time?
Yeah.
How much power does that cost?
Power is shiftable. So there are scenarios where you have abundant power, and during those times you can write through. If you don't have the power, that's when you can.
Because it's kind of the limit. Okay.
And also, this is actually the y-axis power. So you actually need a little bit of power to save the states other than shutting down. But the benefit is we can actually restore the states. So we don't need to go through all the boot up system. I mean, like the loading libraries or something. That actually requires power. So yeah.
Thanks very much.
Hello everyone, my name is Pratyush Patel and I'm a PhD student here at the University of Washington. Today I'm going to present our work on enabling power over subscription for LLM inference clusters in GPU clouds. This is work that I did as a research intern this summer at Azure Systems Research right across the lake. And over there I got to work with a lot of cloud efficiency experts, including Isha, who's right here in the room. So let's get started. As many of you are probably familiar, LLMs have exploded in popularity in the recent past, and there are diverse use cases spanning search engines, chatbots, as well as code generation have led various companies, including Microsoft, Google, and Amazon, to pump in a bunch of money to build new data centers to support these like compute-hungry workloads. And importantly, since the demand for inference far outweighs that for training, since everyone wants to use these in their own products, a lot of these new clusters that we are seeing today are inference clusters. Unfortunately, the problem with building data centers is that it's slow and expensive to do so. And a big challenge here is that of power availability, because the lack of power supply that is needed to run these power-hungry workloads really adds up to the cost as well as the delays for building new data centers. And this is showing up in many cases, including the power infrastructure not being well equipped to support the power delivery needed to run LLM inference. So in this work, we asked the question whether it's possible to deploy more GPU servers in existing clusters today and also do so in upcoming clusters. And to understand how much opportunity is there to do so, we characterized production power consumption for training clusters and inference clusters at Microsoft, and we plotted the peak power consumption of these two clusters. What we found is that although training clusters do end up utilizing almost the entire provision capacity for the cluster, in inference clusters there is almost a 20% headroom, which could be oversubscribed. And this is a great opportunity to go right ahead and deploy additional GPUs in existing clusters themselves. So let's kind of take a look at what that would look like. Let's say you have a cluster which has a power capacity of 100 kilowatts, and that's composed of servers, each of which could have a maximum power consumption of 5 kilowatts. These are clearly very power-hungry servers because they're GPU servers. And in the traditional way in which servers are provisioned today, you might try to fit as many servers as possible within this cluster budget. So that would be about 20 servers. And this is the configuration that, this is approximately the configuration that would be underutilized in practice. So what you could do is you could add more servers in this cluster. And in the common case, that would be a great thing because your power utilization of the cluster would not hit the peak, and you'd be able to run many more workloads in the same power delivery infrastructure that you have. But the problem, of course, is that in certain rare cases, it's possible that the power consumption of the servers might exceed the power budget that you have in the cluster. And when this happens, things go really bad because your cluster can come down if you don't respond to that power increase quickly. And if not, you have to throttle down all of your servers to their lowest power states to ensure that the power delivery infrastructure does not fail. So to prevent that failure modes or to prevent the throttling of all workloads, we really need ways to limit the server power consumption and to do so in a smart manner. This idea itself is not very new in CPU clusters as of today. CPU clusters commonly employ power oversubscription strategies coupled with some sorts of power capping or bandwidth limiting to throttle the CPU power consumption whenever whenever the peak power demand is very high. Unfortunately, this doesn't work very well for GPU clusters because, as you can see, CPUs constitute a very small slice of the overall power consumption in a GPU server. So even if you throttle the CPU in such a GPU server, it's not going to change the power usage a lot. What we really need is a way to manage the GPU power in such settings so that we can safely add more server capacity in existing LLM inference clusters. And this is exactly where POLCA comes in. POLCA effectively manages the GPU power in existing LLM inference clusters. And it does so with minimal performance impact on latency critical LLM workloads. So this was an overview of POLCA. In the rest of this talk, I'll talk about why LLM inference is a promising workload for oversubscription. I'll then describe some of the challenges that we run into in deploying power oversubscription in these GPU clusters, and talk about how POLCA addresses these challenges. And finally, I'll conclude by presenting some analysis results that we ran with POLCA. So let's take a deeper dive into LLM inference itself. Let's say we have this typical ChatGPT-like interface where a user wants to talk to ChatGPT. The user might submit an input prompt, which is then submitted to a model, and the user expects a response. What happens for all of the LLMs deployed today, more or less, is that this user prompt is converted into a set of input tokens, which are then fed into the model. And these input tokens go through a forward pass through the model to generate an output token, which I've denoted here using this orange bubble. In addition to this, the model also generates some state which it caches for future iterations. This output token which is generated can be returned to the user, but it is also used to generate subsequent tokens in the model. So the KV cache and the newly outputted token go back into the model to do another forward pass, and this sequence keeps repeating until the model generates a special sequence known as the end of sequence token. And at that point, the inference is considered to be complete. Now, you might notice that the first token that is generated has slightly different performance and computational characteristics than the rest of the tokens that are generated. So we term the first token generation as something known as the prompt computation because it's computing on this input prompt, and the subsequent token generation as just the token generation phase. And crucially, the prompt phase is highly parallelizable because it's processing all of those input tokens together, and as a result, it's super compute intensive. In contrast, the token phase is much more memory intensive because it relies on the KV cache on each iteration, which it uses to generate subsequent tokens. And these compute characteristic differences also show up in terms of power consumption. So prompt phases tend to be much more power intensive than token phases. And to demonstrate this, I'm plotting this graph which shows the power consumption of the Bloom open source model running on 8 GPUs. The y-axis shows the normalized power draw across all of these GPUs, and the dashed red line is the total TDP across all of the GPUs as well. And what you can see here is that the spiky parts correspond to the prompt phases, and the lower power utilization corresponds to the token phases. And this pattern is not only true for Bloom, we also tried this across a bunch of different open source models, and a similar pattern emerges. Now, when similar patterns are aggregated across the cluster, across many servers, the statistical multiplexing across a lot of them is really what results in this underutilization of power at the cluster level. And because of this, we believe that LLM inference is a promising workload to deploy, to use for oversubscription. So let's take a look at what challenges we might encounter in practically deploying oversubscription for LLM inference. The first challenge really is the deployment mode for cloud GPUs today. Most cloud GPUs, when deployed with virtual machines, end up relinquishing the GPU to the virtual machine so that it's no longer visible to the hypervisor. This is in contrast to how CPUs are virtualized today, where CPU access is present for both the hypervisor as well as the virtual machine. The lack of in-band access from the hypervisor to the GPU basically means that there is no control plane on the GPU to change its power or limit its power consumption when needed. What this limits us in practice is to use out-of-band power management interfaces. But the problem with out-of-band power management interfaces is that they're extremely slow. Just to give you a context of how slow it is, throttling a single server with 8 GPUs can take up to 40 seconds in today's clusters. And this is very much in contrast to the milliseconds that we were discussing a little bit earlier in terms of how much time we have to implement the power throttling decision. So another challenge is that LLM workloads are very latency sensitive. At least the user-facing ones like chatbot interactions or search engines have tight latency requirements, and a power oversubscription mechanism that we deploy needs to ensure that these workloads are not impacted. Simultaneously, there are lower priority workloads that also exist, such as those that do data wrangling, which could tolerate some sort of latency impact. And finally, given that cluster provisioning decisions are done at the scale of a few years, and in this time it's possible that models can quickly evolve, we need to ensure that the power management strategy that is deployed is adaptable to these workload changes, because not doing so would very much limit the utility of the cluster going forward. So let's take a look at how POLCA overcomes some of these challenges. POLCA operates at the row aggregation level in a GPU cluster, as opposed to at the rack level, which is common in CPU clusters. Deploying POLCA at the row level lets it benefit from the statistical multiplexing of inference requests across different servers. And it's also really a coarser granularity for control, because each rack can only have so many power-hungry GPU servers deployed. POLCA also gets priority-based information from the VM allocator, which is assigning LLM workloads to these servers. And this helps it capture the latency sensitivity of different workloads. And finally, POLCA uses multiple throttling thresholds to work with the slow out-of-band GPU power management interfaces that exist. In particular, POLCA has a strong safety threshold at maximum server power, maximum cluster power utilization, which can throttle all of the GPUs to ensure safety. But since this is a very undesirable point to hit, POLCA also introduces additional thresholds which cap lower priority workloads over higher priority ones to manage, to ensure higher priority workload performance. You can find out more details about the policy itself in the paper, and I'll share the link towards the end of my talk. So to quickly go over the results, we looked at how POLCA performs with a 6-week cluster power trace. And this power trace was replicated using open source model based on the numbers that we saw in a production inference cluster. We captured a bunch of different workloads with different prompt input and output sizes. And well, here are the results. So what I'm showing is how well POLCA can oversubscribe existing inference cluster, assuming a 50-50 split between low priority and high priority workloads. The x-axis shows the percentage of servers that we add into this cluster, and the y-axis shows the performance impact on the low priority and the high priority workloads. The dashed red line is the first point at which we incur a power break, which means that all of the GPUs get throttled at 100% cluster utilization, a place that we'd never want to get to. And as you can see, low priority workloads do get impacted a little bit more than high priority workloads, which can maintain their performance consistently despite the fact that the cluster is oversubscribed. In particular, low priority workloads barely get impacted in terms of throughput, in addition to high priority workloads barely getting impacted at all in performance, while oversubscribing the cluster with 30% more servers. So we think it's a promising way to go forward as well. So to summarize, POLCA is a power over subscription framework for cloud LLM inference clusters. In this talk, we saw how power is a key bottleneck for new cluster deployments. We also observed the opportunity how that cloud inference clusters offer to, since they underutilize power. And POLCA exploits this opportunity by enabling GPU-based server power throttling. And it can add many more servers under the existing power delivery infrastructure with minimal workload impact. You can find out more about the paper. It's at this link. And that brings me to the end of my talk. Thank you so much.
Questions?
Yes. So am I understanding the operational model correct, that you have an existing cluster and you're assuming there's real estate in a rack or a rack position is open and you can go in and add more servers there?
Yes.
After it's been operational?
Yes, that is the model. And like space tends to not be as big a problem because each server is extremely power dense. So the limiting factor tends to be power as opposed to like the space available.
And networking is already there?
Networking is something you still have to add. It's not something that we like explicitly considered in this analysis, but it would be something you would.
Yeah, I'm also trying to understand some aspects of it, which is that, are you saying that your power throttling is imposing an upper bound on the power, but it's not actually slowing down the GPU? Is that right?
That is not right. The power throttling does slow down the GPU, which is why we see the performance impacts on the lower priority workloads and high priority workloads. The good part about it is that the performance loss that you incur is not proportional to the power that you reclaim. So the amount of power reclaimed tends to be much higher than the performance loss that you incur in proportionally. So that's something we explain.
Just to add to it though, the throttling is rare, right?
Yes.
It's not like you're constantly running throttling. It's only at certain times of the week or the month.
Depending on what's happening with the rest of the cluster.
Yes.
Got it. Okay.
Yeah, if I could ask Dave's version of this question. Like, are there going to be problems trying to get the throttling to happen within the 5 millisecond time interval?
So the deadline that we at least see at the UPS level from like some of the previous works was at a 10-second granularity. The 5 millisecond granularity, I'm not super sure like at what level of the power hierarchy it shows up at. So maybe that'd be helpful to learn.
The current systems are at 10 millisecond. Like
10 millisecond range. I see. Okay.
Yeah, just similar to the previous papers.
Okay, that's fine. I mean, 10, 5.
Yeah.
Okay. Thanks very much.